Once an AP has discovered, selected, and joined a controller, it must stay joined to that controller to remain functional. Now consider that a single controller might support as many as 1,000 or even 6,000 APs, enough to cover a very large building or an entire enterprise. If something ever causes the controller to fail, a large number of APs would also fail. In the worst case, where a single controller carries the enterprise, the entire wireless network would become unavailable. That might be catastrophic. Fortunately, a Cisco AP can discover multiple controllers, not just the one that it chooses to join. The left figure shows this scenario. If the joined controller becomes unavailable, the AP can simply select the next least loaded controller and request to join it as the right figure actually depicts. That sounds simple, but it is not very deterministic. For example, if a controller full of 1,000 APs fail, all 1,000 APs must detect the failure, discover other candidate controller, and then select the least loaded one to join. During that time, wireless clients can be left stranded with no connectivity. You might envision the controller failure as a commercial airline flight that has just been cancelled. Everyone that purchased the ticket suddenly joins a mad rush to find another flight out. The most deterministic approach is to leverage the primary, secondary, and tertiary controller fields that every AP stores. If any of these fields are configured with a controller name or address, the AP knows which 3 controllers to try in sequence before resorting to a more generic search. When an AP boots and builds a list of potential controllers, it can use CapWeb to build a tunnel to more than one controller. The AP will join only one controller, which it uses as the primary unit. By building a tunnel with a second controller ahead of time, before the primary controller fails, the AP will not have to spend time building a tunnel to the backup controller before joining to it. As a wireless network grows, you might have several controllers implemented just to support the number of APs that are required. A good network design should also take failure and high availability into consideration. It is not enough just to have multiple controllers in a network. What if they are all in use and full of APs? There would not be enough room to spare for a large group of additional displaced APs to join in their time of need. In the commercial flight analogy, there might be other flights departing the airport soon after the cancellation. If those flights are already mostly full of passengers, many people will be left waiting at the gate. This figure illustrates an example network that does not offer enough capacity to fully survive a controller failure. In the before diagram, as you can see, a group of 400 APs has joined controller WLCA, and the group of 300 APs has joined WLCB, as you can see. Okay, and here you can see each controller has a maximum capacity of 500 APs. As long as both controllers stay up and functional, the wireless network should work fine. In the after diagram here, WLCA has failed. All 400 APs that were previously joined to the WLCA will discover that WLCB is alive. So they will all try to join it. But WLCB already has 300 APs, so it has room for only 200 more. That means 200 APs will be able to join WLCB and 200 more will be left out in the cold and with no controller to join at all. This is the result of undersized controllers during a failure. Now let me to explore how we detect a controller failure. When HA or high availability is required, make sure that you design your wireless network to support it properly. Fortunately, Cisco APs and controllers are built with HA in mind, so you have several strategies at your disposal. First, it is important to understand how APs detect a controller failure and what action they take to recover from it. Once an AP joins a controller, it sends keep alive, also called heartbeat message, to the controller over the wired